Hello friends, in this session we will be discussing about the importance of sinusoids. Let's begin. Now see here, let us understand why we love sinusoids. Why we love sinusoid means, for example, the answers people give. Many people have different answers. Some people say that, sir, yes, generation of sinusoid is easy. Generation of sinusoid with different frequencies is easy. Is it so easy? Is it so easy? Let us see. But see here, the people who say this are electronics people, small people. Small people in the sense, those people who work at small signal level. ECE guys, electronics guys. They will say that yes, we love sinusoids because it is very easy to generate sinusoids with different frequencies. For example, we use LC oscillators and all, right? But this is not true. Let us think of another answer. Another answer people give is that, sir, integration and differentiation of a sinusoid is a sinusoid. Let me just write it down. Differentiation and integration of a sinusoid is a sinusoid. Meaning that, see here, if you think of d by dt of sin t, differentiation of, let us say, sin t, what is that going to be? That is nothing but going to be cos t. Right? And if you think of, they are nothing but basically time displaced, what do you say, waveforms. Sinusoids only, no? See here, for example, if you think of sine wave will be like this. If you think of cos wave is going to be like this. Am I right or wrong? So at the end of the day, it is nothing but, even if you think of this cos, it is nothing but shifted version of sine only. Which is the reason people say that yes, differentiation and integration of a sinusoid is a sinusoid. But it is for signals and system faculties. It is for signals and system branch, not for us. Let us say what control system people have to say. Yes. Answer number 3, which people give. Control system faculty says, yes, there are many frequency domain tools. There are many tools to analyze the system in frequency domain. Means tools for frequency domain, if you think of. What are those tools, sir? Bode plot, Nyquist plot, etc. Right. But it is again from a control systems engineering point of view. It is only for CS faculty. But what about electrical people? What about people like us? Because see here, generation of sinusoids is easy. Analog people say that. It is true for them. From analog perspective, it is easy, I can understand. But we as electrical engineers, we deal with bulk amount of power. Bulk amount of power means, sir, huge power. Which means for us, actually generating sinusoid is very difficult. How it is difficult, we will see. We will see that. No worries. Anyways, so for us, but then why we need sinusoids? Why electrical people need sinusoid? Let us see. From our perspective, electrical engineering perspective, we have seen EC guys perspective, control systems guys perspective, SS guys perspective as well. But let us see our perspective. Our perspective is what? See here. We already know that this is electrical engineering perspective, right? Which is very important for us, and this is the real reason why electrical engineers love sinusoid, why we are taking so much of efforts to have sinusoidal waveform. We'll see that. Anyways, what about electrical guys, sir? Electrical guys, if you think of, see here, we already know that 85 to 90% of the loads are induction motors, right? 85% to 90% of loads, or we can also say that 85% to 90% of the generator power is consumed by induction motors. Induction motors, right? So in induction motor, what is the main principle? The main principle is rotating magnetic field, right? And I am going to prove to you that whenever you have sinusoid, balanced sinusoid, in that case the rotating magnetic field is better. And I will also tell you what will happen if it is not a sinusoid or it is unbalanced, and in that case what will be the repercussions on the RMF and what will be the repercussions on the torque of the motor. So we are going to go in very detailed analysis of it, and then we will combine everything. Anyways, let us see. So for electrical people, why we love sinusoids is because rotating magnetic field will be best when it is a sinusoid. That is the only reason. And why? Why we are so much interested about RMF? Because of induction motors. 85 to 90% of the loads are induction motors. Anyways, see here. Now, if you see, we had talked about time to space, right? Time to space earlier. What does that mean? What was the, conclusion at the end? Conclusion was, if I flow 120 degrees time displaced currents through 120 degrees space displaced winding, I will get one rotating magnetic field which will be of constant magnitude and it will rotate around it, right? Rotate with the angle of time, and it will align itself with the axis of MMF in which maximum current flows. Already we know that, right? Basics, already we have learned. Anyways, see here. So let me consider a stator here, for example. This is a stator. Yes. So let me consider a stator. This is a stator. Let me have conductors. This is A. This is B. And let me have C. Of course, there will be A dash as well, B dash as well, C dash as well. It's okay, even if it is understood basically, right? Anyway, see here. We have this ABC. How are these windings displaced? These windings are displaced by 120 degrees. Am I right or wrong? Yes. These windings are displaced in space by 120 degrees. 120 degree displaced winding in space. Of course, in space, right? Now. And what was the rule? What was the property? What was the principle we learned? It was that 120 degrees time displaced current has to be there or not. Means through this one, what should happen? 120 degrees time displaced current has to flow, right? So let us see here. For example, if I am flowing 120 degrees time displaced currents, right, through 120 degrees space displaced winding, let us say these are the currents, and these are 120 degree displaced. So what is going to happen? I am going to get one rotating magnetic field like this, right or wrong, right? And this RMF will rotate in this way, because see here, at first A maximum will come, so it will align with A maximum. After 120 degrees, B maximum will come, so it will align here. After 120 degrees, C maximum will come, so it will align here. So basically it is going to rotate in this particular fashion. Already we know that. Now let us think of if rather than 120 degrees time displaced currents, If I flow 100 degrees time displaced current, let us see what happens. So this particular green, let me think of 100 degrees time displaced currents. In that case, what is going to happen? For example, I have this green here. Let me consider this as same conductor only, right? Same conductor only. This is green, and green is now 100 degrees displaced. In that case, what is going to happen? Of course, I will have an RMF. RMF is going to be there, no doubt, because it is displaced in time, right? It is not displaced by 120 degrees. I agree with you, but it is displaced by some angle, right? So there has to be some or the other RMF. But now, do you think that the nature of the RMF, which is developed because of 100 degrees time displaced currents, will it be same as 120 degrees time displaced currents? What do you think? Will it be same? Of course no. Then how it will be? This RMF, this particular green, which is produced because of 100 degrees time displaced currents, is going to be elliptical in shape. This RMF is going to be elliptical in space. Whereas if you think of this one, this previous, this red is going to be what? Circular. So now see here, focus here, see. In the first case, when I had circular RMF rotating in the space, in the first case, when it was 120 degrees, right? So you please tell me, the MMF here, MMF here, MMF here, MMF here, MMF here, MMF here was everywhere same, right? Or we can think of flux density everywhere. Was it same? Yes, it was same, because it was circular. The same was rotating here. Constant magnitude, if you think of 1.5 times F max, if you remember. Am I right or no? Right. Now, but then what is happening with green? If you just observe what has happened with green, what has happened with this green, if you see here, the flux density here is what? Is more. Here, flux density is less. Here, flux density is more. Here, flux density is less. MMF is more here. MMF is less here. MMF is more here. MMF is less here. So what will be the effects? Now you please tell me one thing. See here. When I am saying that it is 100 degrees time displaced, is it unbalanced or not? 100% unbalanced, right? So let us firstly understand what are the repercussions of those unbalanced currents, and then we will try to understand how can we analyze unbalanced as well, and then how can we have pure sinusoids. Anyways, let us see here. See, focus. Now, the moment I have elliptical RMF in space, the moment I have elliptical RMF in space, what is going to happen? Torque, if you think of torque, torque is not smooth, or we can say that torque is not constant, right? Why? Because see here, everywhere if you see, the flux is not constant in space. The moment flux is not constant in space, at some point torque will be more, at some point torque will be less. I hope you are understanding my point, right? Since this flux is not constant in space, this flux is not rotating at a constant magnitude in space, what is going to happen? Torque produced by this particular machine is going to be what? Not constant. So the torque produces not smooth. Let us see what happens when the torque produces not smooth, which means, see here, let me think of bike, right? There we have IC engine, something called an IC engine. So there I have IC engine, right? Now see here, when I have IC engine, if you think of, what is going to happen there? Let us see. You apply some strokes in the sensor, some power strokes, or some exhaust strokes or something, right? So if you think of, in case of a bike, in case of IC engine, if you think of, what happens is, see, for example, your bike is moving at a speed of, let us say, 40 kmph, linear velocity. Or for example, let us think of that your engine which is there, it is let us say rotating at, let us say, 200 rpm. 200 rpm. So if you think of 200 rpm here, you please tell me what is going to happen. Your bike will move at a speed of 40 kmph. The wheels of your bike will also rotate at 200 rpm, for instance, for example, right? But then what will be repercussions of the torque? Because if you think of here, if I am saying that your speed remains the same, then what is the problem with the torque? Even if the torque is not constant, it's okay, no sir? Is it okay? No, say here, for example, this is the bike, this is the wheel of the bike. If you think of, this is the wheel of the bike, it is rotating here like this, right? What is going to happen? Of course, it is going to rotate at 100 rpm, 100 rpm. Say here, for example, let me tell you this way. This is the road, if you think of, right? This is your bike, wheel of the bike. If you think, it is going to what? Rotate 40 kmph speed, or we can think of 200 rpm, for example, rotational speed, if you think of. So it is rotating at 200 rpm, 200 rpm, 200 rpm. But what is going to happen? See here, it is rotating at 200 rpm, rotating at 200 rpm, rotating at 200 rpm, rotating at 200 rpm. But the moment you apply some strokes, power strokes, what is going to happen? It is going to take some jerk. See here, first it is rotating smoothly, rotating smoothly, rotating smoothly, rotating smoothly, rotating smoothly. The moment some jerk comes, jerk. See here, rotating smoothly, rotating smoothly, rotating smoothly, rotating smoothly, rotating smoothly, rotating smoothly, right? Now what is going to happen? The moment you apply some stroke in the bike, what is going to happen? It is going to go this way. Means basically it is going to have a pressure of power strokes. Or you can say that since torque is not constant, if you think, see here, the speed will be same, speed doesn't change, but the moment torque is not constant, torque is not smooth, what is going to happen? What is going to happen? Wear and tear of the bearings will happen. What are bearings? Let us think of. We know that, for example, think of, let me have a rotor here. For example, this is a rotor, right? And then I have a shaft here, right? This is a shaft. So what is going to happen between this rotor and this shaft? No, there is something called as bearings. Something called as bearings. So now just think of here. This particular shaft is, let us say, rotating at 200 rpm. Right? Now, what is going to happen? It is going to rotate at 200 rpm, but at the same time, it is going to feel some jerks because of torque is not constant. See here, it is going to rotate in this particular fashion only. 200 rpm, right? But at the same time, what is going to happen? This bearing here will have pressure of that torque, because torque is not constant. Just imagine if the torque is constant. Just feel it that the torque is constant. It is going to happily rotate at its speed. But the moment torque is not constant, what is going to happen? Still it is going to rotate happily, 200 rpm. But since the torque is not constant, that is the reason what is going to happen. Wear and tear of bearings will happen, because you will have sudden jerks. I hope you have understood the point. Anyways, let us see here. So bearings. So there will be what? Wear and tear of bearings. Wear and tear, which means aging of the bearings will happen soon. Aging will happen soon. Aging effects will happen soon. Other factor is you may need to maintain the bearings again. You may need to maintain the bearings. Maintenance will increase. I hope you are understanding these all points, right? So basically, if you think of one final thing, what is that? That torque is not smooth if my RMF is elliptical. And RMF is elliptical. Why? Because you are not supplying sinusoidal, which means my generator is not supplying sinusoidal. So if my generator is not supplying sinusoidal currents, if it is not supplying sinusoidal power, or we can say sinusoidal currents, then in that case what is going to happen? RMF produced will be elliptical. RMF produced is elliptical. That is the reason what is going to happen? Torque is not going to be constant, or we can say that torque is not smooth. The moment torque is not smooth, what will happen? Jerks will take place. The moment jerks will take place, what will happen? Wear and tear of the bearings will happen in case of motor. I hope you are understanding it. So if wear and tear happens, what is going to happen here? Wear and tear happen means what? Aging effects will come, and at the same time maintenance problems will come. Means you may have to maintain it periodically, right? So that is the importance. Now student may ask me, sir, yes, we have understood what is the importance of sinusoid, but what happens if we have unbalanced currents like this? Unbalanced current like this. Yes, whenever you have unbalanced current, right, in that case what you do is, see here, those things, those unbalanced voltages, unbalanced currents, those will be analyzed in a subject called as power systems. Power systems. In that we will be discussing about some unsymmetrical faults or something like that. In that we are going to face what? Unbalanced voltages. And so whenever we are going to face unbalancedness, unbalanced voltages or currents and currents, those will be dealt in power system. You know, some symmetrical components and all will be there, and then the you know, we will be able to analyze unbalanced things as well. Anyways, for time being we have understood that why sinusoidal is important for us. Now let us see how can we produce sinusoid. Let us see. So now let us see how we can have induced voltage sinusoid. Because see here, we have understood that it is very important for us to have sinusoidal voltages, currents also, right? So in order to produce sinusoidal voltages, what can be done? What can be done? Let us see. If you think of importance here, importance was what? Torque is not constant in case of non-sinusoid. So in order to make torque constant, and to avoid wear and tear, what do we want? We want sinusoids. Anyways, let us think of here. See here. We know that E conductor which is there is proportional to B. Means induced voltage in a conductor is proportional to the flux density. Am I right or wrong? Now see here, this is flux density. Means now what I am trying to say is, see here, what we can do in order to have E conductor as sinusoid, means induced voltage in a conductor to be sinusoid. What can be done? Just think. If I somehow make this flux density sinusoid, if I somehow make the flux density in the air gap as sinusoid, then of course induced EMF in the conductor will become sinusoid. So what will be our approach? Our approach will be very simple. Step one will be what? Step one will be to make field flux as sinusoid as possible. See here, step one is what? To make the field flux as sinusoid as possible. Why? Because if field flux is sinusoid, since it is proportional to EMF induced will also be sinusoid. I hope you are understanding the point now. So our step one, our first step will be to make the field flux as sinusoidal as possible. But the fact here is, see here, it is not so easy. If you see here, to make the field flux as sinusoid as possible. Is it possible? Is it possible? You will come to know later in the immediate next sessions. But right now, let me tell you one thing. To make this field flux as sinusoid as possible, it is not possible. Means it is impossible to make exactly sinusoid. To make flux density, or you can say to make flux exactly sinusoid, it is impossible. Why it is impossible, we will see. Now, let me think of harmonics. Actually, what happens is people think that harmonics is something so great. No. Harmonics is very simple. Harmonics is very simple. Believe me. What is harmonics? Let us see. See here. There was a scientist named Fourier. What did he say? Whenever you have a periodic waveform, that periodic waveform can be represented in terms of as a linear combinations of sinusoids. You will not understand anything. Let me tell you. See here. For example, if you have a periodic waveform like this is let us say t, time t, or let us say omega t. Right? Now, this particular waveform, which is periodic in nature, right? This particular waveform can be represented as a linear combination of sinusoids, which means here I can represent this same blue with some sinusoid here. But if you think of this sinusoid, red is not equal to blue. Why? Because blue is non-sinusoid, which means this red, which is nothing but also called as fundamental component, right? Fundamental component. What is the meaning? Let us see. If you think of here, when non-sinusoidal given non-sinusoidal periodic waveform completes one cycle here, so this particular sine wave also completes one cycle, which means it is called as fundamental component, or we can say that component which is having frequency same, right? Anyways, so let me think of some other components also, because see here, this particular blue is not equal to red, right? So in order to make them equal, what I need to do? Linear combination of sinusoid. Means there will be some more components here like this, some more components here. This is second harmonic. Why it is called as second harmonic, sir? Say here, second harmonic means what? What do you say? This one, red. When red completes one cycle, which is called as fundamental component, my green, this particular green completes two cycles, two cycles, right? So it is called as second harmonic. Similarly, I may have third harmonic. Here, and so on. All are sinusoids, right? So what I am saying is, what we want, we want only this fundamental component. That's it, right? Because this particular fundamental component is nothing but the pure sinusoid, right? Now, when this fundamental component is added with some harmonics like second order harmonic, third order harmonic, fourth order harmonics, and so on. So whenever this particular fundamental component is added with some harmonic components are nothing but sinusoids whose frequency is different than the fundamental component. That's it. That is the only thing about harmonics. That's it. These are also sinusoids only, but the frequency is, we can say, multiples of this one fundamental component. Anyways, see here. So what are we interested in? we want only fundamental component, but at the same time, what else we have? We have some other frequency components as well, right? Which are called as harmonics. So what is going to happen? This fundamental plus some harmonics will give you some non-sinusoid. Yes or no? Right. This component plus harmonics will give you non-sinusoid. We want only what? Fundamental component. So see here, when I am saying that it is impossible to make exactly sinusoidal, see here, when I am saying that it is impossible to make flux exactly sinusoidal, which means it will still remain non-sinusoidal. We will try our level best to make it sinusoidal, but it will not become exactly sinusoidal, which means there will be fundamental component plus some harmonics as well, so we have step 2 for this. What is step 2? Step 2 is here. What is the step 2, sir? See, step 2 will be what? Step 1 will be to make the field flux as sinusoid as possible, but it is impossible to make it exactly sinusoid, right? So what am I going to do? Now I will try to make induced voltage sinusoid. We can say induced EMF sinusoid. You must be remembering in your what do you say, colleges and all, you must have heard something about distribution factors, something about pitch factors, Kp and all, right? That is nothing but to make induced EMF sinusoid. We will discuss about it in detail, don't worry. So this is what it is. Now let us think of step 1. See here. Now see, step 1 means what, sir? Step 1 means we have to focus on the field. Step 1 means we have to focus on the field. Now from the previous discussions we know that in case of a synchronous machine, the armature which is there, armature is placed on stator, and field is placed on rotor. Am I right or wrong? Right? So already we have discussed about it a lot in the previous session, that why we have armature on stator in case of AC machines. We have seen that. Anyways, we are going to only focus on the field. Why? Because step 1. So step 1 we are only going to focus on field. So now see here, when we are talking about field, it is on rotor. So if you think of in AC machines, we have 2 rotor structures. What are they? See here, we have 2 structures of rotors. What are those structures? Number 1 is, let us say, cylindrical, and other one is salient. See here, cylindrical means, see, structure is going to be like a cylinder like this, and there must be something at the back, right? Active length will be there, means like this. For example, it is a cylinder. If you think of this particular part which is there, this particular part of the cylinder is nothing but this one. Yes, here if you think of, here also we have some slots. Similarly, here also some slots will be there. And if you think of here, there has to be some active length at the back. So at the back there will be some active length like this. So at the back you will have some active length here like this. This is nothing but active length of that particular rotor. Anyways, let us erase this. We don't need this. So this is nothing but the cylindrical rotor. Now see here, if I have, for example, 2 conductors on this rotor like this, if I have 2 conductors, let me just place dot here, let me just press cross here. What is going to happen? Cross and dot, which means flux is in this direction. If I am sitting in the air gap will be outside the rotor here. If I am sitting in the air gap, my observation is that flux is outgoing from the rotor piece. So since flux is outgoing from the rotor, this becomes north pole and this becomes south pole of the rotor, right? Similarly, there is another structure. What is that? Let us think of this. So see here, basically this particular dot current, cross current which is there is nothing but what? IF current only, right? IF current. IF is what? Field current, already we know. Similarly, if we think of here I am going to have this winding on this. Why? Because we are going to use what? We are going to use electromagnets only. We are not going to use any permanent magnets. Anyways, let us think of IF current flowing here like this. The moment IF current is flowing here, what is going to happen? What is going to happen? See, you have this one. Flux is going to be upwards. Flux is going to be upward means what? From here, if you think of this is going to be the structure of the rotor. From here, if you think outgoing flux will be there. Flux is outgoing, which means this becomes north pole and this complete part becomes south pole. I hope it is clear. But now let me tell you one thing. So we have to analyze this cylindrical rotor in detail. Also, we have to analyze salient rotor in detail. Why? Because in case of synchronous generator, if you think of, because see here, synchronous machine which is there, it is actually used for the purpose of generation, and induction motors are used in case of motoring operations. Anyways, see here, when we talk about these two rotors, cylindrical rotor as well as salient rotor, will be used in synchronous machines. Whereas in case of induction machines, we don't use both of them, we use only cylindrical. And in case of synchronous, we use both of them. So you see here, in case of induction motors, we are only going to use cylindrical, whereas in case of synchronous machines, we are going to use cylindrical as well as salient. So in the immediate next sessions, we are going to talk about cylindrical rotor, and after that we will be talking about salient rotor, and then at the end we will understand which rotor has to be applied where. Thank you.